Hey guys, this is Ikarus. This is a 3D printed, thrust-vectored electric ducted fan rocket, for the lack of a better word. It's basically a 19mm EDF with batteries, flight controller, receiver, motor controller, basically all the minimum requirements for flight strapped to it, plus 4 independently controllable thrust vectoring vanes. I'll give you a quick demo of how this flies. It's generally similar to a normal quadcopter, and then go over the engineering challenges in actually making this work.
The spacecraft of a Sputnik or something.
Well, hovercraft. The U.S. Air Force built something like that. It's a vertical takeoff and landing.
Right.
1950s or something. Next project, build one with 2 or 4 jets.
Oh. This whole project started when I got one of these 90mm EDFs off of AliExpress. I actually saw they had a package with the motor controller and the EDF for about $70, so I couldn't resist picking one up. I didn't even know what I was going to do with it at the time. The first thing I built was actually just a handheld blower. It's just this frame with the fan mounted on it and the motor controller and a servo simulator. And I was just using it as a leaf blower and used it to clear snow off cars a few times, which was actually very effective. But it had about more than enough thrust to lift itself up. Like, it would, if you let this thing go, it would fly straight up. So I figured maybe we can actually turn this into a flying machine. This EDF runs on 6S LiPo, so that's about 22 volts, and draws about 60 amps or so at full throttle. It's rated for, I think, 2.8 kilograms of thrust. It measured about 2.4 or so. As expected, it doesn't quite meet its spec, but it's good enough for this application. The craft has 4 2.2 amp hour 3S batteries, and they're wired in a series parallel arrangement for 6 amp for a 6S total at 4.4 amp hour. Other than the batteries that make up about 63% of the craft's weight, we have a micro CC 3D flight controller, which is running Libre Pilot. And as we'll go over later, I had to modify the firmware on this to get proper stable control. There's an FR Sky telemetry receiver, and on the other side there is the motor controller that came with the EDF. Everything is mounted to this 3D printed piece. In fact, everything on this that isn't off the shelf is 3D printed. The piece has all the mounts for all of the servos, mounts for the batteries, which just strap in. The strap just goes through a hole in the 3D printed piece. And of course, the flight controller and the motor controller also are mounted to this single piece. You can see the print for this here. This still has all of the support material, so it's a bit hard to see what's going on in there. Here are all the 3D printed parts. These are the thrust vectoring vanes. There's 2 versions of this, the one in mirror image because of how the main frame is laid out. These are the landing legs, which just bolt directly on, screw directly into the frame. And to get a little bit better view of the frame, this is a failed 3D print that I just test mounted a servo onto. And see how the landing legs work. These are actually surprisingly strong. The legs have not broken. I've actually cracked the frame, so that's actually the weakest point. Here's a better view of the inside of the nozzle. It tapers down with a constant area as you go across, so the outer part tapers in less than the inner part. And there's this part where the vanes mount in like this with a rod going through. This nozzle is designed to give the smoothest airflow possible around the motor, and also keeps the motor exposed a little bit so that it gets cooling from the airstream. I put a lot of thought into the design of the thrust vectoring vanes. There are 4 independently controllable vanes to give full control of pitch, roll, as well as the rotation of the craft, or any combination of these all simultaneously. And the shape is so that they can come together like this without actually hitting each other. The vanes also have the pivot point is not at the very edge. It's in the middle slightly, so that as the vane turns and air is hitting it, say from this angle, some hits in front of the pivot point, some hits in the back. And this results in much less force being required by the servo to move them. In fact, with this design, there's a little bit too much in front. So when the servo turns the vane, it's actually having to pull back. The vane wants to pull itself all the way over, so the servo power required is very minimal. It could get away with much smaller. These are micro servos. You could probably get away with much smaller servos on this because of how the vanes are designed. The shape of the frame in this area is designed so that when the vanes are in this position, vectoring air sideways, there's a good amount of area for the air to come out. If this just continued around at the full level, this would largely block up that air opening. I've been working on this for about the last 6 months, on and off in my spare time. By far the hardest part of getting this to fly was getting the control working right. The actual construction of the craft was pretty quick over a few weeks, getting 3D prints working properly, getting everything to fit. But yeah, the biggest problem was control. Initially I tried to just fly this in free flight. Here's some video from that. Oh, that was instability. Yep, I think the gains are too high. As you can see, there were some problems with instability. It was in the last shot, it was doing something like this. And that sort of points to the culprit here, which is having a single, very high-speed fan that has a gyroscopic effect. So when the craft turns, it wants to be pushed in the opposite, 90-degree opposite direction by the gyroscopic force. Normal quadcopters don't have this because they have 4 rotors and the gyroscopic effects all cancel out. And one solution here, the easy solution here, would be to have 2 counter-rotating fans on top of each other spinning at the same speed. And that would completely solve this gyroscopic problem. And this fan, I believe, in hover spins at something like 27,000 RPM, and at full throttle it goes at 35 to 38,000 RPM, so faster than a Dremel. It is very, very powerful and very loud. I played around with the control loops a lot while trying test flights like this over quite a while, and couldn't find anything that would make the craft at all stable in hover. To try to get around this, I initially thought that I just didn't have the control loops set right and I needed to adjust them, so I built a frame, shown here, that just held the craft steady so it could move pretty much only in one axis, and I used that to set the PID loops as best as possible. Got very good control. It would generally hold exactly where it was told to hold, but when it flew, it had this the same rotational problem. At this point, I realized that it would take some modifications to the flight controller firmware to get this to work, and I would also have to build a gimbal to do this testing in, rather than trying to fly it in free flight. So I built a gimbal, and I figured it was interesting enough to start filming all the development directly. So at this point we will rejoin my past self for the story of getting this thing fully stable and in flight. To evaluate the control response of the craft, I built this gimbal frame. This allows the craft to rotate in any direction extremely freely. It's supported on ball bearings on all sides. So this, and then also routed the cables to minimize the torque effect of the cables themselves. So this should allow a proper evaluation of the control response. So, operating in the gimbal frame, you can very clearly see how the control response is incorrect due to the gyroscopic nature of the fan. When the craft attempts to pitch directly forward, it actually turns slightly, and this tends to cause the entire craft to sort of oscillate around like this, and you could see that in the test video I showed earlier. So, to try to fix this, I'm going to disable the control of all of the feedback control and just have the stick directly control the movement of the fins, so we can put a control in and see sort of what angle the top of the craft will reach. We're expecting it to move just like this, but it's actually going to sort of move in some angle relative to that. And then what I'm going to try to do is basically rotate the thrust vector of the thrust vectoring vanes so that when you push it forward, it actually pitches straight forward rather than at some other angle. I'm hoping that will correct the control problems. That's not a complete solution because it's making an assumption about the rotational speed of the fan, but hopefully it will be enough to get the craft off the ground initially. As you can see there, the control response with open loop control is completely unusable. Basically, initially the craft starts moving in the direction you command it, and then due to the gyroscopic force or precession, it then sort of turns, and steady state turns 90 degrees to the angle that you were commanding it to go. So I figured because it was moving 90 degrees to the direction I wanted it to go, I tried just rotating the control vector 90 degrees. But the problem there is you don't just need a 90-degree application of force. You have to apply force a little bit in the direction you want to go to accelerate the craft. And then once the craft is moving, you then need a vector to the side at 90 degrees to sort of keep it steady state. So basically what the control system has to do is to initially accelerate the craft, so to pitch the craft up. You initially have to apply some pitch up vector, like this, and then once the craft is rotating, you have to apply a pitch sideways to compensate for the gyroscopic precession. So I had a bit of a thought on how to do this. And what I've done is modified the flight controller firmware to apply a portion of the angular rate to the control at 90 degrees. Let me just put it into that mode and I can show you what I've done. Here's the change I've made to the flight controller code. What I've done is taken the roll and pitch angular rate, turned them 90 degrees, and then multiplied them by a adjustable constant. This is something to do with the cruise control function of this flight controller, which I'm not using in this, so I've just taken over this parameter cruise control power delay comp. This is accessible from the UI and is easily adjustable. That's used to adjust the amount of this compensation applied. With this function enabled, you can clearly see how the vanes vector 90 degrees to the angle that the craft is turning at. You can see the vanes compensating for the gyroscopic effects in this video as the craft rotates. To set the amount of this angular rate compensation to apply, I just spin up the fan and then push the craft forwards and backwards so that and then observe how much it rotates in the opposite axis. So in this case, we're adjusting the roll, turning the roll, and observing how much pitch changes like this. And if we do this with the fan running, we can see that because I've adjusted that the cruise control power delay comp to minimize the amount of pitch change when changing the roll. Now that the gyroscopic precession compensation is working, the conventional control mode seems to work pretty well. The control you just saw was after spending some time playing around with the PID loops. These are the settings I ended up with, along with a bit of extra derivative compensation on the rate stabilization. So the control response isn't as fast as I would like, but I don't think there's much better we can do with this system just because of this response speed of the servos. When the craft accelerates, the servos can't accelerate instantly to apply the gyroscopic precession compensation right away. So there's a little bit of when you command like a pitch, there's a little bit of a roll applied, but I don't think it's too bad. I'm going to take this out of the gimbal and give it a try actually in free flight. Okay, that's not right. So the problem seems to be that a failsafe is occurring. I've replaced the motor controller with just a servo, so you can see that changes. I've set the failsafe to go to 100% instead of 0, and if we move the control surfaces, eventually, at some point, we're going to see that servo move up. Yeah, that should not be moving. I'm not touching the throttle. See, like now that's touching the throttle. It shouldn't be doing that, so there's some sort of software problem going on here. Also, when I turn it to the direct control mode, this doesn't happen. Another thing I noticed is on this flight data thing, this event is going off, and when it goes off, there were problems with UAV object events or callbacks, so the software modification I did may have caused some sort of problem, so I'll take a look into this. So I think I may have figured out the problem. Reading the manual for the transmitter, it actually says that PPM, which is a mode that I'm using to transmit all the channels over one signal wire, is not properly or fully supported in this transmitter because of the high number of channels. And depending on the amount you move the channels or what position they're in, the PPM signal may sort of overrun all the channels are sent sequentially as a pulse down the one wire, and they all it might cause an overlap if there are too many channels. So I'm just going to go back to the old method where you have one servo port per channel. We'll see if that fixes it. The way I figured this out was happening was when I moved the sticks around a whole bunch, the I/O input came up and it gave an error that, let's see if it'll pop up here. No, yes it will. Failed to update one or more of the accessory channels. So yeah, we'll see if going back to the normal mode works. Going back to PWM mode has solved the problem as far as I can tell. I can move this around as much as I want, and no errors come up at all, or no cautions. Yeah, let's give this another try. I think this is a balance problem. There's all the wires I added on the far side are causing it to fall over. I'll try adding some weight to the receiver side. Okay, that was a better result. Got some control at least. Okay, so I probably need to play around with the control loop a little bit, but that is much better results than before. Oops. And that covers development up to this point. My future plans for this are to redo the frame so that it supports the batteries without tape. I want them to just be able to slot in from the top. I also want to try running it with fewer batteries, because I have a feeling that running 2 instead of 4 batteries is actually going to increase the flight time, because the fan will take a lot less power. The power goes up with the square of the craft weight, so removing the batteries may actually increase the flight time, and it'll also, of course, it'll have the same amount of power, so it will have better performance. I also want to put a shroud, sort of like the engine cowling on a airliner turbofan around it, just so it's more aerodynamic and everything's contained. Ultimately, I'd like to do a second version with 2 counter-rotating fans, get much higher performance. My ultimate goal would be to beat the 0 to 100 meter UAV speed record, which I believe is currently held by this guy on YouTube. Have a look at the link in the video description. He got, if I recall, 2.8 seconds, 0 to 100 meters, and I think a craft like this will be able to beat that, because it's capable of flight so much faster due to the very high airflow speed out of the ducted fan compared to props. If you'd like to build one of these yourself, have a look in the video description. I'll have a link to a website with all of the 3D models and a list of parts to buy, etc. I'd like to thank my Patreon supporters for providing funding for making this possible. I'd also like to make an announcement for a contest we have for Chronos camera owners. We have a contest to win a Pelican case with foam. If you own a Chronos camera, make a cool video and submit it to us. The winner who has the best video will get a free Pelican case. And at this point, I'll show all of the bloopers and problems while trying to get this thing to fly. I hope you enjoyed this video. Thanks for watching. This is the world's worst RC car. A lot of torque there. Well, it's nerve-wracking because it initially has a backwards control response.
Not quite the desired response.
Nope. I need to put a guard on that. Oops. Almost. That was close. Oh, that was instability. Oops.